In this video, we do some exercises from chapter 4 to enhance our understanding. Obviously, the most important thing from chapter 4 for you is to compute various risk measures, in particular, VAR and TVAR. Those two are the most important thing. And if you have additional time and energy, you should also study a little bit more on distortion risk measures, in particular pH and Escher Ch4. So that's what you need to know from this chapter. So the first question I want to solve from exercise 4.8, okay, it's from the textbook. So if you don't have, let me type the question. Suppose I have a constant that is between 0 and 1, and the distribution function of the loss x is, okay, so we have something interesting. So it's c times this x for when x is greater than or equal to 0, less than 1, and 1 when x is greater than or equal to 1. So here we have this rather strange shape, and we want to know the distribution function, the expectation, the VAR, and the TVAR. So the most important thing, obviously, is to figure out what kind of distribution it is, because C is something we don't know, right? We only know it's between 0 and 1, but other than that, we actually don't know too many details of it. So our first job is obviously to figure that out. So, but before we do anything, let me draw a brief graph to quickly show what it looks like. Okay, so this is x-axis. I'm trying to draw the distribution function, because this is distribution function, so or CDF. So it grows. So this is obviously a straight line with slope less than 1. So assume this is 1. Okay, so it grows. Okay, and the important thing is, okay, I use a huge hole to denote it's empty point, and then obviously eventually it will go to 1. That's because this is a CDF function. So this is the graph, right? From this graph, what can you tell? Because that is the most important thing. We need the part A. We just need to plot this. This I just did. From this, we obviously see there's a jump, right? So from this, I know the probability that equals 1 would be 1 minus this point, right? So this is where I jumped at 1. So I will have a jump at this point. And between 0 and 1 is smooth, right? It's a straight line, so I can differentiate. Right? So this should be greater than 0, less than 1. Although this put equality, I mean, for continuous paths, it doesn't matter, right? So here, what we have is a mixed probability function and probability density function. So use small f to denote. So if you want, you can put 0 otherwise, if you want, right? Okay, from here, we want to know the expectation. Do the usual thing. We have a continuous part, x times the density. So c dx plus, we have a summation part, but here we only have single point. Okay, it's very easy to see the result. This is obviously c times half plus 1 minus c, so it's 1 minus half c. Okay. By the way, we can do it in the most general way, because we know we can write this as, right, it's non-negative, so it goes from 0 to infinity. If it's a general random variable, just write from negative infinity to positive infinity. Okay, so from 0 to 1, we know it's x, inclusion. So we know this is dcx, right? So the question is, at 1 you have a jump, so it's exactly what you jump. So I use delta instead of d because this is a discrete point, and beyond 1 there's no change, right? Because beyond fx, it's just a d of 1. Okay, d of 1 is 0, so this part is 0. This part is obviously, you can write it as x times c dx. So this is the change. No, not x, is 1. So it's f1 minus the, okay. This means the value at 1, this means when you approach 1 from the left-hand side, the view calculus, right? So, but obviously, approach 1 from left-hand side, which means your point gets closer and closer to 1. Eventually, it gets ultimately close to this empty point, which is 1 minus c. Not 1 minus c, it's c. In the graph, it's c. The distance is 1 minus c. So that's why here, here is 1, here is c. So that's why, they are both are the same. So if you have trouble understanding the second general way, you can just leave it. You can use the standard definition to get it done. Next, let's do the VAR. Okay. Once I have the distribution function, y is easy, right? My distribution function only takes 2 parts. So let's do the analysis. Okay, for this part, we know the left point will give me c, so that is the maximum probability, right, I can get on the continuous part. So for any delta less than c, any delta less than c, because what I mean is, if you are not comfortable with this, what you can write is, for this part greater than or equal to 0, less than c, for any x between 0 and 1. Okay, so that's why I need to discuss delta less than c. Obviously, delta has to be greater than 0. In this case, all I need to do is simply equate my CDF to the level delta. From there, I get x is delta divided by c. So that is my quantile. So my var at delta would be delta divided by c. Okay, but for any delta greater than c, less than 1, I have to use 1, right? Because there's nothing in between. So solved. So if you want, you can put it into a nice piecewise form. So when this delta is greater than 0, less than C, if it's ever greater than C, less than 1, or if you want, you can put 1 if you want, right? But that's, I mean, here it doesn't really matter. Okay, then we want to calculate the TVAR. To calculate TVAR, if you already solved for VAR and is in a nice piecewise, what I would suggest you to do is to apply this definition. Because we know TVAR is the average of all the VARs that is between delta and 1. Okay, so let's do, because soon we will realize the other case, there's nothing you need to do. So now I will need to separate my integral into 2 parts, from delta to C. Okay, so for this part, my quantile, my VAR, I just calculated, right? So it will be the level divided by C. The level here is y, so it will be y divided by C dy. From C to 1, my VAR is 1, so that is the result. So then I just need to compute, right? So here I would be 2c in the denominator, y squared, so c squared minus delta squared plus 1 minus c. So if you want, you can try to simplify, right? The other side I don't need to discuss because it is 1, right? Then doing average, I still get 1. So, but nevertheless, we can write it out, right? So if this is, right, because it's very simple, you only have 1 piece. So for anything greater than C, so even you are trying to do the average, you will get this result. What else I want to do? I think there's another important thing of what we have for the Ch4 transform. So let's review again. So here we end this example. Here, let's take a look at, I think we can do, what do we have? Let's do 4.10. So 4.10, here we have some pH transform. So basically what we want to do is we are trying to apply the results of proportional hazard transform risk measure. Okay, we have several different distributions. I believe we already did some of them in the lecture. Let's do another one. So this is uniform. Okay, so immediately what we can write is the survival function of it, right? And we know x is between 0 and 2b. If you want, you can put equality. So we need to apply pH by applying the pH transform we get the new survival function S tilde, which is the whole to 1 raised power 2 1 over gamma, and the gamma is greater than 1. Okay, so this is the result, right? And in order to get the risk measure, we compute the expectation of this new random variable. And since my x is between 0 and 2b, so I integrate from 0 to 2b, 1 minus my this term over, then it's 1 over gamma dx. So my job now is to calculate this integral. So obviously I'm trying to replace anything that is standing in my way. So I use that to replace. So then when my x is 0, my y is 1. When x is 2b is 0, so later on we will need to flip it up. So it's 1 y, 1 over. So now I need to figure out what is dy. dy equals negative 1 over 2b dx. So that means I have negative 2b dy. So here let's put this in front and let's cancel the negative. We flip the order of integral. Right. Then it's very simple. You get the result very quickly. So obviously this is a power function. Then it's 1 because it's from 0 to 1. Right. So from there, let's times by the parameter gamma. Then you get 1 plus gamma. Okay. So this is the one of the first one, I believe. Okay. There are actually many more to do. The second one is exponential. I believe we already did exponential in the video. The third one is Pareto. I think we also did. What we already know from exponential and Pareto is they give us back the same family, so you don't need to do this. How about I ask you to try something different. Try binomial. Okay, so far we only focused on continuous distributions, right? So try something discrete and try binomial and puzzle and to see what happens. Okay, I leave this to you to try. Right, remember when we have exponential distribution, after we apply pH transform, we remain in the same family. So the new x tilde is also also exponential, and we also did the same question for Pareto, and we later on claimed that x tilde is also a Pareto with a different parameter, right? So I encourage you to try these two. I actually have a little bit more of to say, but it's rather technical. So let me finish this video here.